matrix rank, and because the philosophy here is very similar to tensor rank and non-negative rank and PSD rank and CP rank and all the other ranks that you're going to hear about in the opening lecture by Pablo Parillo in the workshop. Okay, so let's recall that a matrix has rank 1 if it's the product of a column vector and a row vector. So I'm going to take that as the definition, and that's a very good definition of what it means to be a rank 1 matrix, outer product of two vectors. So just to make sure, suppose I have a vector 2, 3, 5, column vector times a row vector, 1, 4, 6. Then this product is a 3 by 3 matrix of rank 1. Okay, so first row, I just multiply this by 2, I get 3, 6, 8. 4, 7, 9, and then I multiply it by 5, I get 6, 9, 11. Okay, so that's a rank 1 tropical 3 by 3 matrix. I'd like to give you 3 definitions of what it means to be the rank of a matrix. The first definition is 5, 3, 1. That's the Barvinok rank. The Barvinok rank of a matrix, and let's say my matrix now is a D by N matrix. I'll give you a D by N real matrix, and the Barvinok rank is the smallest R for which M can be written as the sum, tropical sum, just to be clear, as the tropical sum of R rank 1 matrices. Okay, that's one reasonable definition of rank, so that's equivalent. So equivalently, my matrix M, so it's a D by N matrix. It has rank, Barvinok rank R, if it can be factored as the product of a D by R matrix times an R by N matrix, like this. Okay, that's equivalent. Okay, so if I have a factorization, tropical factorization, a low rank factorization of rank R, I'm going to say the matrix has Barvinok rank R, at most R. Okay. Second definition is 5, 3, 2. That's the Kapranov rank. So these are Russian mathematicians. Okay. Barvinok is a mathematician at the University of Michigan. Kapranov is a mathematician at Yale University. So the Kapranov rank of M is the smallest rank of any classical matrix. Old-fashioned classical undergraduate matrix, A, D by N matrix in some field K with the valuation which tropicalizes to M. And today, let's just keep it a little bit simple. So K is a valued field of characteristic 0. Let me just for now assume, so for example, Puiseux series. Okay, so K is a field with the valuation, and let me assume for a moment the field has characteristic 0. So the Kapranov rank is the smallest rank of a classical matrix to which my tropical matrix can lift.
And I fix this field for the rank. Does the notion depend on
it will depend on the field. Yeah, so for example, if K is, So if k is just the complex number with a trivial valuation, then there is no, But if you have a, you could imagine, right? You could imagine here, replace this 3 by pi, 3.14, blah, 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 blah. Then you can't lift it, right? Because pi is not allowed as an exponent here. But you could imagine, allowing real exponents. So you can, if you take there's one field that will do it. I think it's there are various fields. So if you allow, real exponents here, then you can fix one field. But so what you want is you want to have real exponents in your field. Okay, and that's all. Let's not worry about it. These are technicalities. Okay. Yeah. If you have a rational matrix with rational entries, then Puiseux series is good enough. Okay, here's another definition. Only 3. Okay, 3 definitions of matrix rank. The third definition, so definition 533 in the book to be, that's the tropical rank. So tropical is not the name of a Russian mathematician. So the tropical rank of my matrix is the largest positive integer r such that m has a tropically non-singular R by R submatrix. Okay? Now what does it mean for a square matrix to be non-singular? It should not lie in the hypersurface defined by the tropical determinant. So non-singular means there's a unique assignment of jobs to workers. Right? So the minimum is attained uniquely. Okay? That's what it means to be a non-singular matrix. Okay? Okay, so we have these 3 notions of rank. Let's just do a little quiz. I think we have time enough. So quiz for the audience. For which x is this matrix tropically singular? Just, we practice a little bit, So here's a matrix. How about 1, 2, 3, 3, 2, 4, 6, 3, 6, x. Okay, so this is clear. So it's my matrix. 1, 2, 3, 2, 4, 6, 3, 6, x. So there's a unique real number. Hint, it's an integer. There's unique number x. There's unique number x that makes this tropically singular. What's that x? It's not 9. Okay? 2. 2 has been suggested. So let's try. X equals 2. Well, if we have 2 here, then what's the tropical determinant? So then the tropical determinant is 6. That's uniquely attained. So for x equals 2, that's a non-singular matrix. Give you a hint. You can calculate the determinant. And then, that's a linear polynomial, and then you find the unique root of that linear polynomial.
X equals 6.
6, right? X equals 6, right? So the determinant of this matrix is 4x plus 10, and then the unique root is 6. Okay? Very good. Okay, so that's how it works. Let me give you a theorem. (5, 3, 4). We always have the following inequalities. For any matrix, the tropical rank is the smallest. The Karpanov rank is at least as big as the tropical rank, but the largest is generally the Barvinok rank. Okay, so we always have these inequalities. So tropical rank less or equal Karpanov rank, less or equal Barvinok rank, and they can be both strict. So both of these inequalities can be strict. So classically, they're all the same. Classically, for matrices and tensors, actually, they are all the same definition. Classically, they're all the same definition. But tropically, they diverge, right? So there's going to be 3 different notions, and they're all interesting. Now, how are they interesting? Well, they're interesting depending on your geometric preferences. Let me write down 3 fields of mathematics. So one field of mathematics could be combinatorics. Another field of mathematics could be algebra. And another field of mathematics could be geometry. Okay? And this class somehow is at the interface of these 3 fields. And these 3 notions of rank reflect these 3 fields of mathematics. So if you like combinatorics the best, then you should like the Barvinok rank the best. If you like algebra and algebraic if you like algebra the best, you think like an algebraist, then you should like Karpanov rank the best, right? Because this ties it in with classical algebra over a field. But if you like geometry, if you think geometrically and you have no problem visualizing 4-dimensional polytopes, then this is the notion of rank you should like the best, right? So this says that the combinatorial definition is less than the algebraic definition, is less than the geometric definition. Let's explain this. Yes?
For any variation.
For any, yeah. So that was Rainer's question. Let me say, I'm going to take a field just to get rid of this. Okay. I think this is a bit of a, let's do this. Okay. I'm going to make a field C parentheses T. So this is I'm going to fix one field once and for all. I'm going to make a field, okay? I forgot the name. Field of generalized power series. So this is a field with power series in T with real exponents. And you have to do a little work to turn that into a field. So I'm going to make a field. It's complex power series in T with real exponents and complex coefficients subject to some fine print. That's it. That field will be good enough for today. Okay? I'm going to change the field in 30 minutes, but let's keep this field. Okay, let me explain this a little bit. Okay, just to kind of get a feeling, what's going on. Why are these ranks different? How do you compute these ranks? And so on. Let's start with a geometric interpretation. So let's sort of wind this up from the point of view of geometry. So let's start with tropical rank, and let me explain why that's a geometric notion. So let's say P is the image of my matrix M. So that's a tropical polytope. In RD mod 1. Okay, so I have a D by N matrix, so the image is the tropical convex hull of N points in D minus 1 space, as we learned in the first lecture today, in the first hour. So the image of P, of the matrix. Now classically, right, what's the notion, right? The rank of a matrix is the dimension of the column space equals the dimension of the row space. Classical math is lame, right? The row space, the column space have the same dimension. How lame is that? Tropically, they are the same polyhedral complex, period. The row space equals the column space with all color and all decorations almost, okay? Now that is important for people like Spencer and Kang-Jin who study divisors on curves, graph curves, syzygies, on canonical curves, and so on, right? Because if you study that tropically, what happens is that in this matrix, so here we took an m by n matrix. So if you study divisors on curves tropically, what happens is that the space of divisors that are linearly equivalent to a given divisor is such a tropically convex set, except one m is very small and the n is very big, like sort of infinity-ish. Okay? So if you study divisors on metric graphs, things like canonical curves and their divisors, this becomes very relevant, except you're going to have sort of 3 by a million matrices, or 5 by a billion, or something like that. Okay? Anyway, let's come back. So we have our polytope in D-1 space, and the dimension of P is the tropical rank of M, and there's a -1. Okay? The tropical rank is -1. The number of tropical vertices, so that's the tropical rank. So let me rewrite like this. So the dimension +1 is the tropical rank. The number of tropical vertices is the Barvinok rank. Okay?
So the dimension of the polytope is the dimension of the biggest cell.
The dimension of the biggest cell. Okay? So this is a two-dimensional polytope. The tropical convex hull of 3 points in the plane, the image of a 3 by 3 matrix of rank 3 in every sense. It's a full rank matrix in all definitions. Right? So, well, if this is 3, then they're all 3. Okay? So now you can sort of see, right? So if you have a tropical polytope, if you draw the image of your matrix, then the dimension of the polytope +1, that's the tropical rank. That's a geometric notion. The number of vertices, that's the combinatorial notion. Right? The number of vertices, that can be bigger. Right? The number of vertices can be bigger than the dimension +1, but it's at least the dimension +1. Right? For a polytope, the number of vertices at least the dimension +1, but they can be different. So for example, let's do an example. Suppose you have, this point. Let me move them in special position now. Right, so I give you a 3 by 3 matrix, and the picture is like this. Right, so now I have a red point, red point, blue point, yellow point. They're collinear. I have 3 points on a line. Right? So this convex hull is a one-dimensional polytope with 3 vertices. We're clear? It's a one-dimensional polytope with 3 vertices. Okay. So the corresponding matrix is going to have tropical rank 2, but Barvinok rank 3. Right? The Barvinok rank is the number of tropical vertices, 3. Right? The tropical rank is dimension 1 + 1. That's 2. So just to drive this home, let's do a little exercise together. Okay, so in-class exercise. Determine all 3 ranks for this matrix. Okay, let me give you Let's take a couple of minutes, 2 to 3 minutes. So I give you this 3 by 3 matrix that is the classical identity matrix, but of course it's not the tropical identity matrix. So I'd like you to tell me for this matrix what is the Barvinok rank, also Brank, the Kapranov rank, Crank, and the tropical rank, Trank. What are they for this matrix? Okay, what's the tropical rank? 2, right? This is tropical rank is 2. That's a singular matrix, right? In the assignment problem, the minimum is attained twice, but it's not a rank 1 matrix. So it's singular, so the rank is at most 2. It's not rank 1, so the tropical rank is 2. What about the Barvinok rank? Barvinok rank is 3, right? I just proved it to you, right? So in the projective plane, right? So this is 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So the Barvinok rank is 3. You cannot factor this as a 3 by 2 matrix and a 2 by 3 matrix tropically. And our friend at NIMS, who lectured on Monday at 11 o'clock, the numerical PDE guy, he might like to know about this. Please follow up and speak to these people. Please, 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 pretty please. Okay, Kapranov rank. Rainer, what do you think the Kapranov rank of this matrix might be?
2.
Kapranov rank is 2, right? So what you need to do is you need to find a classical matrix over some field that has this valuation, and I have my own matrix. Okay, so for example, let's take this one, T, so A, right? So we need to take a classical matrix, T, 1, T squared plus T minus 1, 1, T, 1, 1, 1, T. Okay? Okay, hopefully the first, okay, this is supposed to be a singular matrix. Why is it a singular matrix? So the first plus the second should be 1 plus t times the third row. Okay? So this is a singular matrix, and this matrix, you know, the entries have this valuation, right? So on the diagonal we have valuation 0, 1. The off diagonals have valuation 0. Okay? So this is a lift, a classical matrix. That's a lift of this tropical matrix, right? So it's a classical 3 by 3 matrix, and these field elements have the correct valuation.
So what do you mean by valuation?
Valuation, okay, so let's take this field. So these are power series. So by valuation, I mean the largest exponent that you see. So like in the undergraduate lecture, we called it epsilon. We would call it T. Okay. The yellow matrix is this matrix. Okay. That's Kaplanov rank. Now, how do you calculate these ranks in general? Okay, suppose you want to design an algorithm. Okay, and this has been studied. So there have been papers written. So if you like complexity theory, you can read papers on the complexity of calculating the Barvinok rank, tropical rank. These are interesting questions. If you don't like complexity but you like computing, you can also do it, right? You can write Sage code that will take a matrix M and calculate these ranks. So how would you do that? Well, the Barvinok rank, that's a sort of a combinatorial problem. So it turns out that that's sort of a tricky combinatorial problem. To actually decompose the matrix, that's a very much sort of graph theoretic type problem. So it's a non-trivial, combinatorial problem. The tropical rank, well, in principle, you calculate the tropical polytope, right? If you have the image, then it's the dimension of the largest cell. So that's a polyhedral calculation. So it's sort of, the kind of thing you lie on the floor, you look at the thing from below, and then whatever dimension you see, sort of calculation. Okay? So that's a polyhedral calculation. Well, let me here talk about the Kaplanov rank. That's sort of most interesting, sort of algebraically. I like algebra. So here's what you do for the Kaplanov rank. We use Macaulay 2. We use the fundamental theorem of tropical geometry, which is now 2, 3, 4 in the current notes, and Grobner bases. So I'm just going to throw this at you. This may not be comprehensible to everybody, but I will try. So what you do for the Kaplanov rank is you look at the determinantal ideal of minors of a matrix of unknowns. So these are the r plus 1 times r plus 1 minors. Right? So this is not a good algorithm. Even if you're as brilliant as Rainer, it's not so easy to find these lifts. Right? So finding lifts is not so easy. This is not a recommended algorithm. So to calculate the Kaplanov rank, to say what is the smallest rank of a classical matrix, that's hard in general to find that lift. In my opinion, that's an opinion, it's easier to use an alternative characterization of the tropical variety, namely, it's a set of all weight vectors such that the initial ideal is monomial free. Okay? That we can test, right? So the tropical rank says, well, the tropical rank is R if we are on the tropical variety, if my matrix is a point on the tropical, the Kaplanov rank is R if my matrix is on the tropical variety defined by the r plus 1 times r plus 1 minors. That's the Kaplanov rank. That's exactly the notion of Kaplanov rank. So we form the ideal of r plus 1 times r plus 1 minors. We calculate the initial ideal with respect to M of that ideal. M is the matrix whose rank you're interested in. You define the ring in Macaulay 2 with weights given by your matrix. So you make a matrix, you use that matrix as the weights, right? So you make a polynomial ring in 9 variables, and these variables have weight 1, 0, 0, whatever these things are. You make these the weights, and then you negate, okay? Because Macaulay uses max convention. So you take the weights, and then you calculate the initial ideal, right? And the question is, does this contain a monomial? Okay, so the question is this monomial free? Okay, that's the question. If that is monomial free, then the rank is bigger than R. Okay, so a matrix has Kapranov rank bigger than R if and only if that initial ideal contains no monomial. How do you test whether an ideal contains no monomial? Well, you saturate against the product of the variables. Right? So there's several ways to do that. Okay, so you have this ideal, you want to test whether it contains no monomial. If it contains no monomial, the rank is bigger than R. Then you go by divide and conquer, right? Then you take a larger value, and that way you calculate the Kapranov rank. Okay, so what have we done? I've sort of indicated these three different notions of rank, and I've given you a sense of computing them. So the Barvinok rank is sort of hard. It's a combinatorial notion. It requires combinatorial algorithms having to do with graph theory. The tropical rank is a polyhedral computation. You need to calculate the image of a matrix, which is really calculating a polyhedral subdivision of a product of simplices, and then we're interested in the largest dimension of an interior face of that subdivision. Okay, that's a polymake calculation. The Kapranov rank, which is the most algebraic notion, I think we can approach best by Macaulay too. Okay, and I've shown you that the Barvinok rank can be bigger than the Kapranov rank in this case, but I haven't yet shown you an example where the Kapranov rank is bigger than the tropical rank, and that's coming now. Let's look at this matrix. That's a 7 by 7 matrix whose entries are 0, 1s. So this has a particular structure. It has the structure of the Fano plane. Let me draw the Fano plane for you. So this is the projective plane over a field with two elements. So that has 7 points and 7 lines. Let me label the points. 1, 2, 4, 3, 6, 5, 7, and this is also a line. Okay, the circle is also a line. So 7 points and 7 lines. Okay? And this yellow matrix is the incidence matrix of points and lines. So for example, so here, I have the lines, and here I have the points. Okay, so point 1, 2, and 4 forms a line. 2, 3, 5 forms a line. 3, 4, 6, and so on. Okay, so that's the point line incidence matrix of the Fano plane. Okay, so this is in the notes. That's equation 5, 3, 7. Okay, so this matrix has a tropical rank 3, but Kapranov rank 4. Okay. You don't believe me? Well, let's run Macaulay too. Make a matrix of unknowns, a 7 by 7 matrix of unknowns, and look at the ideal of 4 by 4 minors. Macaulay 2 will do that actually. You look at the 4 by 4 minors of this matrix, calculate the initial ideal with respect to these weights, and it contains a monomial. Okay? That's it. Why is the tropical rank 3? Well, you check, right? So there's every 4 by 4 matrix here is tropically singular, but there's some 3 by 3s that are not. Okay? This has. Now the explanation for this comes by matroid theory. Via matroids. This is explained in the notes in Theorem 5.3.21, which says if you take any matroid whatsoever and you make an incidence matrix between the points and the hyperplanes, the elements And so the hyperbolaeans are the complements of co-circuits. Right? So you make a, let's say the points from the row, the elements of the matroid are the rows, and the co-circuits are the complements, and you put a 0 whenever an element is in the co-circuit, and a 1 whenever the element is not in the co-circuit. Then the tropical rank of that matrix is the rank of the matroid. And the Kapranov rank has that same rank if and only if the matroid is realizable in characteristic 0. Okay? Well, we set things up so that this is over characteristic 0. So if I had allowed characteristic 2, right, then the rank here would be 3. But you can have some other matroids. You can have matroids that are not realizable over any field, such as the Pappus matroid or the non-Pappus or non-Desargues matroid. Then you really have examples between what tropical rank differs from Kapranov rank, even if you allow finite characteristic. Okay? But according to our definition, since this is a matroid of rank 3, this matrix has tropical rank 3. Since this matroid is not realizable in characteristic 0, the Kapranov rank is bigger than 3. Okay? That's the content of this theorem. It's not a difficult theorem, actually. Okay? I'd like to do 2 more things. Are there any questions? We have 14 minutes left, and I have 2 more brief topics. Yes?
In this algorithm, the initial term means terms who has minimal weight or maximal weight?
Minimal weight. Because we're using the min plus algebra. So this is the ideal generated by all leading forms. Okay? So I take all infinitely many polynomials in this ideal. For every polynomial in this ideal, I look at the initial form with respect to lowest weights. I calculate the ideal. I look at the ideal generated by all those initial forms. And the question is whether that contains a monomial or not. But Macaulay 2 will do that for you. Okay? Yes, question.
When the 3 of the ranks are
Coincide? Sometimes. Small examples, yeah. It depends on the matrix. Depends on the matrix. Okay. I'd like to address 2 more questions. So Barvinok rank is sort of a different notion. As I said, it's very combinatorial. It's closely related to the notion of non-negative rank. So many people now study a notion of non-negative rank of a matrix, just like tropical convexity really mirrors and eigenvalues mirrors Frobenius-Perron theory. So non-negativity really is sort of very tropical in some sense. Tropical is sort of a theory of non-negativity. And Barvinok rank is a combinatorialification of the notion of a non-negative rank. There are lots and lots and lots of good questions in this field, and interesting from many points of view. But let me move away and ask a question about the other 2 notions of rank. So for which values of R, D, and N? So this is sort of a version of your question, Jensuk. So if I have R, D, and N, for which values of those 3 integers do tropical rank and Kapranov rank always agree? So what I mean is, let's suppose I fix D and N and R. Okay? When is it the case that every D by N matrix of tropical rank R also has Kapranov rank R? Okay? So that's the question. Well, we believed for a while that the matroid theoretic obstruction, the one I depicted by the Fano plane, was the only obstruction. Right? So whenever you have a non-realizable matroid, then that gives you a range of R's and D's and N's, and you can make counterexamples. And we believe that that was the only way to make counterexamples, but that's actually false. So there was people worked on this for a while, And this is sort of summarized now. And this is Sheetov's theorem. Okay, that's Jaroslav Sheetov, one of the 3 authors who will be here next week and whose writings are on Oprah's to read list. Okay, so Sheetov's theorem, 5.3.25 in the notes. And it's stated as follows. The set of minors, r plus 1 times r plus 1 minors of a matrix, of a D by N matrix, is a tropical basis if and only if something is the case. Okay? Now, what is tropical basis? Tropical means that the tropical variety is cut out by the tropicalization of those polynomials alone. Okay? And in our context, that is exactly the question, right? So the reason Kapranov rank can disagree from tropical rank is because the minors do not form a tropical basis, right? So if the Kapranov rank is 3, if the tropical rank is 3, and the Kapranov rank is 4, that means the 4x4 minors, the tropical 4x4 minors, are not enough to cut out, set theoretically, the tropical determinantal variety, right? It's not enough to require that the 4x4 minors are tropically non-singular. There's some other equation unearthed only by Macaulay too, whose tropical vanishing we need to require. Okay? So the minors form a tropical basis if and only if r is less than 2 or r plus 1 is the minimum of D and N, or R is 3 and the minimum of D and N is at most 6. Okay? Anyway, this is a bit hard to read, so let me sort of say in English. So the 2x2 minors, that's trivial. So the 3x3 minors, they form a tropical basis. That's always true. And the maximal minors of a matrix form a tropical basis. So the 3x3 minors form a tropical basis, and the maximal minors form a tropical basis. The 4x4 minors of a 7x7 are not a tropical basis. That's the final counterexample we just saw. And this says there are some exceptional, situations. So I would recommend that you take a look at exercise 8 on page 260, and there's an explicit example that's non-matroidal. So Sheetov gives a 6x6 matrix of tropical rank 4, but Kapranov rank 5, not coming from matroids, as far as we know.
What is that?
What does that mean? Well, it's a situation where so if you're in a regime where R is the rank and N is the number of elements of a non-realizable matroid, then you can build such examples. That it's not a tropical basis. But here you're not in this range, right? So because every rank 4 matroid on 6 elements is realizable. Like every rank 2 matroid is realizable. Okay? So in this range of rank 4 and 6 elements, everything is realizable, but still there's this example, and I have no idea how Sheetov found this, but there's only one way to find out. Okay? So last topic, fresh off the press. The Daily News. Eyewitness news. Okay? I'd like to tell you about a new paper that I just learned about this morning. We already actually posted around May 20th, but it escaped me. I had too much fun being in Korea, so I failed reading up on the daily archive posting. So this is archive 1405, 4161. So the authors are four authors. Alamigion, Banchimol, Stéphane Gobert, and Michael Josvik. So Josvik is the developer of Polymake. And the paper is called Long and Winding Central Paths. So this is a paper in tropical linear programming. Well, you can imagine what tropical linear programming is. You already know what tropical polytopes are. You know what tropical linear functions are. Well, you know, linear programming is the computational problem of maximizing a linear function over a polytope. Right? So tropical linear programming is pretty much what you think it is. Maximizing a tropical linear function over a tropical polytope. Okay? Now, they apply this in this paper to solve a problem in classical linear programming. So this uses tropical methods to disprove a conjecture. Well, this is the paper, title of the paper. Long and winding path, long and winding central paths. To disprove a conjecture called the continuous Hirsch conjecture. So this is a certain conjecture that was formulated by Desar, Terlaki, and Zinchenko not so long ago in 2008. Okay? Let me explain. Okay? So what's the Hirsch conjecture? So the Hirsch conjecture was a conjecture that was stated in the 1950s. It had to do with the classical simplex method for solving linear programming problems. So in linear programming, there are two fundamentally different approaches to solving this. One is called the simplex method. The simplex method is you want to find the optimal vertex, say the highest vertex. You start at any vertex, and you make a sequence of paths along edges. You go from vertex to neighboring vertex to neighboring vertex, and so on. And you locally improve until you can't improve anymore, and then you're at the optimal vertex. Okay? That's called the simplex algorithm, and that's been the workhorse of linear programming forever. Okay? After World War II, the definition of forever. Okay? So, well, one question early on was asked, well, how many steps do you need? Well, certainly an upper bound is the diameter of this polytope. Right? So you look at the edge graph, and you ask, well, what's the diameter of the graph? Right? What's the largest sequence? So you want to find two vertices whose combinatorial distance is as far as possible. And if this is a d-dimensional polytope with n facets, then it was conjectured that this diameter is at most n minus d. That was a long-standing open problem. That was disproved by Paco Santos quite recently. This is an exciting recent development in combinatorics, and there's a whole story. Okay? So the other approach for solving linear programs is by interior point methods. So interior point methods, they do something completely different. They say, let's go right in the center of this polytope to something called the analytic center. You zoom right into the analytic center, and then you do a numerical path continuation method, a homotopy method, from the analytic center to the optimal vertex along a curve called the central path. Okay? Now there the question is also, how many steps do you need? Lots and lots of people work on this. And there it's not so much the diameter in a graph, it's something called the total curvature of the path that matters. So if the path is very, very curvy, the total curvature is high, then you need many steps in the numerical algebraic geometry method. And there was a very parallel conjecture, like n minus d. There was a Hirsch-like conjecture for the central path formulated by these people. I worked on it, we couldn't do it, but these guys did it. So they found a counterexample. But this counterexample was found by tropical methods. And since we're gearing up for an optimization workshop, and since some of you, and 3 of our speakers, are interested in using tropical methods for optimization, I just wanted to advertise this paper to you. So please, on your device, if you have reception on the hike this afternoon, take a look at figure 3 in this paper. So this is a 3-dimensional, they show you, this is a 3-dimensional polytope that disproves this. A 3-dimensional polytope over an ordered field, but now this has to be an ordered field with evaluation. So this is something called the Hardy field. This is some suitable series, Okay, this is some, suitable ordered field. There's some suitable field, ordered field with evaluation, and they draw the polytope. So if you go take your device, you look at this paper, you look at figure 3, there's a 3-dimensional polytope that is used to disprove this conjecture. In figure 4, it shows you that it's done by having a tropical line segment with many, many bends. So the way this is set up is that you have a line segment that bends a lot, right? So this comes, of course, can imagine a line, a tree in higher dimensions, right? You could have a segment, a 1-dimensional polytope, the convex hull of 2 points that wiggles and bends a lot. So based on such an example, they're able to lift that to this classical field. This field is set up to allow for convergence, really, because you want to set it up. So when we do Puiseux series, we cannot guarantee convergence. So you really want to have a field that lets you work with convergence. So they set this up, and then they get the counterexample classically. Okay, that's it for today. Please join the hike, and next Thursday we'll talk about semi-definite programming and sums of squares programming with lots and lots of exercise in the afternoon.